is lossy transmission lines. So this is still a good assumption for many cases, but this is the sort of the real situation. So I think of this more as like, at high frequency, or long distance. And those really depend on, it's a combination. Okay, if you had, you're trying to, put a AC voltage across the country, and the AC voltage is only running at 60 hertz, you have to worry about the loss in that transmission line. Okay. All right, so just a few words. We're not going to get into the details of the analysis much right now. Hopefully we'll get back to it later, but it's two different things that cause this parallel resistance and the series resistance. So let me call this, let me see if I have a name for these guys later on. Let me call this R, and let me call this 1 over G. Resistance 1 over G, okay? So G, the 1 over the parallel resistance, that comes from dielectric resistance. This is just sort of for your background info. So let's say a dielectric is our insulator. So if you have a wire, let's say if your transmission line is like the simplest transmission line, it's a twisted wire pair, right? Each wire has got a metal at the center, then it's got some kind of an insulation on the outside of the wire, right? So when you're twisting those, you get some kind of a repeatable inductance and capacitance. Well, that insulator between the wire is like a pretty good insulator at low frequencies, but as you go higher and higher and higher frequencies, it actually gets to be less and less of a good insulator. You start getting a small current going through the insulator. Same with the coaxial cable. For your cable or in the lab, you basically have a metal line at the center of your coaxial cable. Then you have a metal on the outside of your coaxial cable, and what's in between is this insulator material. If you actually cut it, you'll see the insulator material. Don't cut it, the lab cables, but you'll see an insulator, and it's made out of some dielectric, okay? And that dielectric starts having this dielectric resistance or dielectric loss if the frequency gets high enough. And that's what sort of this parallel resistance comes from. The series resistance that comes from the resistance of the material, whatever material is. So that's the metal line resistance. So if your metal lines are made out of copper, aluminum, gold, whatever you want to call it, none of them is a superconductor. A superconductor is a metal or some material that has zero resistance. Okay, any kind of real conductor, if you take, it'll have very low resistance, but it'll have some resistance in series. And as it turns out, that's also frequency dependent because you have this weird effect called, maybe it's called the skin effect, and hopefully we'll come back to this later, skin effect. And it turns out that if you look at a piece of metal, as you're in low frequency, if your signal is low frequency, you're using the entire sort of like cross section of the metal for your conduction of your current voltage and whatnot. As the frequency goes up, you start getting less and less of the total cross section, more and more of that stuff gets bunched up towards the outer part of the metal layer. Okay, that's called a skin effect. Again, we'll hopefully come back to that to talk about that. That's an electromagnetic effect. But so anyway, the upshot of what I want to say is that these resistances come out of the fact that we're dealing with like real stuff, real dielectric and real metals. Okay, so it's part of our thing. So okay, so now let me see what I want to say. Did I say all of it? Yep. Okay. Is that everything? Okay. So now we're going to start the analysis of how do we analyze this. Okay. So this is another analysis warning. Okay. So because now I have inductors and capacitors and resistors, if you guys remember, inductors are, so if I think of the impedance of an inductor, it's not the load in, sorry, it's got too many, so I'm just going to write it out. So impedance of inductor is J omega L. Okay, so the impedance of an inductor is actually a function of the frequency. Okay, and the impedance of capacitor, whoops. I think I started with decent handwriting this morning and it's been going downhill since then. Impedance of capacitor is 1 over J omega C. You guys are all good with that, right? So basically to mix inductors and capacitors with resistors, I'm going to basically assume that I'm sort of operating at a single frequency, and I'm going to use these impedances. Let me plug in my computer. Just give me 1 second, guys. Keeps going dark on me. Okay, so, all right, so let's look at the inductor first. Okay, J omega in phasor notation is the same as d by dt. You guys remember that? We talked about it, maybe you don't remember it, but basically in phasor notation, d by dt is equal to j omega. Okay, so for example, if by looking at an inductor equation as V is equal to L di dt. That's a basic equation for an inductor. Okay, so in phasor space, it just look like V is equal to L j omega. It looks like j omega L sort of I in phasor space. That's sort of like an advantage of phasor space. So we're going to use that as an advantage. So let me draw the transmission line with all this stuff in here. So we have R for each section. We have a j omega L. We have our G, or 1 over G. And then we have j omega C. So this is our new section of a transmission line. So I've added the series and parallel resistance to our transmission line. And this just keeps getting repeated. Whoops. This keeps getting repeated over and over again. And for each section, we're going to have a current of, in phasor notation, I of Z. So let's say this is Z. And then we're going to have a V of Z. And this point here is Z plus delta Z. So this is a Z axis. So here we're going to have I at Z plus delta Z and V at Z plus delta Z. So these R's and G's, just if you guys remember, are when we're talking about, because we're talking about sections of the line, the inductance or capacitance, their units are in terms of inductance per meter, capacitance per meter, and so will the resistances and the, in this case, P. So the resistance units are in terms of ohm per meter, and the G, which is 1 over the resistance, is in terms of Siemens per meter. Okay, and now, so we had LC, and now we're adding RG, and so these are the primary constants of a transmission line. And are we ready to go with that? And so we're just, for now, we're just going to assume these are given to us. Okay, you'd need basically electromagnetic equations to figure out how to calculate those. Okay, so now I'm going to do the same thing that we did when we just had, yeah, Jed. So now we're going to do just the same thing we did when we just had L's and C's. We're going to get an equation for the voltage as a function of Z, and an equation for current as a function of Z, and take the derivative and come up with a waveform solution that meets those two functions. That's a solution to those two functions. Are you good, Jasmine? Yeah, okay. So I'll keep going. So now we're going to again look at what happens when delta z goes to 0. So imagine if these guys get smaller and smaller and basically sort of gets into a continuum of inductance, capacitance, resistances. So we end up with the equation of the change in voltage respect to Z is minus R I hat plus negative J omega L I hat for each section. That's just Kirchhoff's voltage law when you have those two. Okay, so, and I'm going to call that equal to minus Z I. So this is just impedance, okay? And this is the same as L di dt. If we had not shifted it over into phasor space. So now because we're in phasor space, I can just replace that with minus j omega L, or j omega L, okay? And then all simultaneously, the current has an equation of the form with respect to looking at each one of these sections, do minus GV hat minus j omega C V hat. And I'm going to call that minus Y V hat. So I'm defining Z. I guess that's a thing for Z, I guess, is R plus J omega L, and Y is getting defined as G plus J omega C. Yeah.
So when I look at a party, I can see for a change in V over impedance, you're just summing the inductor and the resistor, right? For changing the current, you're summing capacitor and resistance, like that way in parallel.
This is so this is 1 over the resistance.
Yes.
Yeah. So can you say that again?
I just don't see it on the circuit, the math you're doing right
You don't see how I'm just sort of summing these guys up?
now. Yes.
Okay. So remember Kirchhoff's current laws, okay, says that the current at the node has to be the same. So basically, it's not like the voltages, it's the currents at each one of these. So basically what it's saying is there is a current going here, okay? That's this guy. So this is coming from KVL. This is coming from KCL. So it says I have a current, it says I have a current going this way, that guy, and I have a current going this way, that's this guy. Okay? So the difference between the current coming here and the current going out, that's this delta di dz. So this difference between these two currents is the current going through here and the current going here. The sum of those two is the difference between these currents. Is that good? And then this guy is saying the difference between the voltage here and the voltage here is the drop across this plus the voltage drop across that. Does that make sense?
Yes, because when you said change of Z is equals to like, oh, it's zero, actually we're still like at the source, but I see.
This is now we're looking at, just imagine if you're in the middle of the transmission line. So we're talking about a transmission line itself now. So we worked through the source and the load and transmission line. Now I'm talking about what happens if the transmission line is lossy. So I'm back to just looking at small sections of the transmission line in the middle of the transmission line. Are you guys good with that? Yeah? So back to the transmission line and just the lossy transmission line. Okay. So I'm going to take this is, you guys probably don't remember this, but we did this for the LC transmission line, is I took the second derivative of this dVdz and then managed to plug in dIdz. I'm going to do the same thing. Okay. So basically, the second derivative of dz ends up being, so if you just look at this and this and this, I'm going to take the derivative of this with respect to z, and I'm going to take the derivative of this with respect to z being the distance. Remember, I'm keeping these z's as capital Z impedance, so anyway. So minus z di dz. So I just took the derivative of both sides. Here and here. And now I'm going to plug in this di dz for here. I'm going to plug this guy into here. And so I'm going to get d squared b dz squared is minus, or it's going to be plus, let me keep it from getting confused. It's minus z times minus y v. So z y v. And then I'm going to call gamma is equal to z, I'm going to call gamma squared z is equal to z times y. So d squared v dz squared is gamma squared v hat. And I'm going to call this guy propagation constant. Okay, guys, so this, when we saw this last, when we had this d squared v, this squared, the second derivative with respect to z is equal to the thing itself, etc., that gave us this wave function type solution. So we still have that wave function, yeah.
So is that v squared or is that r?
Which one are you talking about?
The zy?
Sorry?
The z, is it r squared equals zy? The propagation constant?
Oh, here?
Yeah.
No, this is gamma.
Oh.
It's like a new, I don't know how to write
That's the
gamma.
definition, right?
Yeah,
Gamma equals z.
gamma. With my handwriting, you guys are gonna be in trouble. So this is gamma again, gamma squared. Yeah, Jasmine.
Why did it
Oh, just the way they define it, because it's two impedance multiplied by each other. Oh, this should be, sorry, this should be squared, right? You're saying why shouldn't it be squared? It is squared, it should be squared, sorry. But gamma is called a propagation constant. Yeah. No, sorry, gamma squared is the propagation constant. Okay. Your expressions say it all to me.
I think I missed what Y was.
What is what y was? Y was the effect of having some kind of a resistance in parallel with our capacitance. So now we have a loss. Okay, we have a lossy transmission line that has a series resistance and a parallel resistance for each section. The parallel resistance comes from the dielectrics being leaky at high frequency. And the series resistance comes from our metal being a real metal that has a real resistance. Okay, so we summed up the resistance, the series resistance, and the inductance, and impedance and inductance, and called that Z. And we summed up these two and called it Y. Yeah. So the summary of what I'm doing is I'm doing something exactly like we did before when we just had L and C sections. Remember, for a lossless transmission line, we just had L and C. We didn't have these two resistors here. I'm doing exactly the same thing, except now I'm summing up. I'm throwing in the resistance, calling it capital Z, and I'm summing up this resistance with the capacitor and calling it capital Y. But the methodology is the same. At every point, if you guys remember, we figured out a KVL at every point, and then came up with an equation for what the voltage waveform would look like. And at every point, we did a KCL, and we came up with what the current would look like. Okay. And we used that to come up with this wave equation that defined how stuff would go through the transmission line. Everybody with me? You guys remembering this? Good stuff. Okay. Questions? Yeah, Jasmine.
Could you say that CY is equal to DI over DZ?
Can you say that again?
Could you say that CY is equal to DI over DZ? Or is it negative 5V?
Can you say that again?
CY is equal to negative 5V. DI over DZ is equal to negative 5V.
Uh-huh.
Down. Down. Yeah.
Uh-huh.
Between there and the next step.
Between here and here.
Yeah.
So I just plug this guy in. This dIdZ is minus YV. So I plug this in for that.
Okay. Okay.
So I'm solving these two equations simultaneously. Okay? This is like the same thing we did for when we just had L and C. Okay? Except now we just have this gamma squared, which is called the propagation constant. Okay, and then this guy, so in general, we're gonna have, because before we just had L and C, okay? L had j omega in it, in the numerator. C had j omega in the denominator. And the magic of that was when you multiply them together, you just ended up with a real number. And that real number, so our characteristic impedance of a lossless transmission line was real, and we had a lossless transmission line. Right? You guys with me? Now, we have a real and imaginary part. The fact that we added these resistors means generally this is going to have a alpha plus j beta form. Don't forget about what alpha and j beta is for a second. Okay? But basically you're going to have a complex impedance or a complex impedance solution. Wait, sorry. I'm going to put this as gamma. So we're not just going to have a real impedance. We're going to have characteristic impedance. We're going to have a real and imaginary characteristic impedance. Okay? And this is called the attenuation coefficient. And this is called the phase coefficient. And so when we have this kind of equation, we said, oh, this has these type of solutions that are called waveform equations. We didn't actually solve it. We said these waveform equations are a solution to this. And they look like as waveform as, let me just call it general solution. General solutions that look like e to the plus minus alpha z times e to the plus minus j beta z. So before, when we had just the capacitance and inductance, we didn't have this. We just had this minus j plus j beta z. And the minus j beta z was the waveform going in the right direction, and the plus j beta z was the waveform coming back. We didn't have this before. Okay? So look at what that does. When I'm stepping through as z is changing in this part, when you're looking at the e to the j beta z, when I'm just changing the z, when I'm just changing that, it's just changing the phase. So going back to the example, as we're going down the transmission line, as z is increasing, I'm just changing the phase of my waveform. Okay? If you just look at this function, as I change the amplitude, this imaginary part is not going to change the amplitude. You guys with me? But now when we added this resistances and end up with this lossy transmission line, we added this exponential that no longer has the j in it. This is actually, as I increase z, this is going to be a real exponential alpha times z. Means my amplitude is actually going to start going down as I go in the forward direction of transmission. So by adding these resistances, we get an actual loss in the amplitude of the waveform as you go through z. Okay, so generally, what happens is, if I was going to draw the transmission line, And imagine in the lossless case, I would have this wave function that would go through, and if I looked at the wave function at the input waveform at different points, this is different points in the z direction, I would just end up with different phases in my sine wave. It would just be different phases, right? As j omega, it's e to the minus j beta z. So at different points, I just see different phases. What happens is, in the case of a lossy transmission line, is not only do I see the phases stays the same, but I'm going to start getting a loss. Whoops. I'm going to start seeing something like this. I'm going to get an actual loss. And this envelope, so this envelope of loss, so this is coming from e to the minus alpha z part of that solution. But it didn't affect the phase, the added resistances. So the artifact of the equation, so again, we have this e to the minus alpha z. So v is sort of proportional to this e to the minus alpha z. Yeah.
Is that equation above this graph? Is that a general solution?
Yeah, it's a general
Is it a
solution.
general solution?
Yeah.
And what is that in front of the alpha z? Is that a plus minus?
Yeah, it's plus minus. So these are plus minuses and plus minuses. Okay? So you end up with e to the alpha minus alpha z, e to the minus j beta z. That's a forward going wave. And e to the plus alpha z, e to the plus j beta z is the reverse going wave. Yeah.
No, we still don't have the imaginary part, so why is the phase not changing?
Oh, sorry, the phase, sorry, what I meant to say is the phase is changing going through the transmission line, but our equation for how the phase changes is the same whether you have a lossy or lossless transmission line. But so the fact that we threw in resistors, a lossy transmission line doesn't affect how the phase changes as you go through the transmission line, but it does affect how the amplitude, how the amplitude changes. Okay, yeah, Daniel.
So for e to the alpha z, why did you say plus or minus? Because if it's plus, then it's expanding out, but we're
Yeah.
calling for losses,
Right.
so it would always be negative.
Well, the thing is, you're kind of seeing what the waveform's doing as you're going in that direction. You know what I'm saying? That
And
makes
how do we
sense?
even get e for that? Do we just say that's the assumption that we're saying that the damping factor is for that wave?
Sorry, can you say that again?
Are we saying, like, how did you get e as a solution? So you said e to the minus alpha z.
Yeah.
How did we get e for that?
How do we get
Just-
it,
is
a
that an assumption
solution?
We're saying for like what the damping factor, what it is? Like, how is it going down? Out of that exponential.
So when we did the, let me just take you guys way back, because I did the same thing for you guys. Let's see if I can find it. Way back. So what Well, we had the same type of equation for the lossless case. Okay, do you remember that? Huh?
I don't remember that on the amplitude side. I was thought.
Yeah, the amplitudes weren't there. You're right. The amplitudes weren't there. But we ended up saying that this has a solution of that form, assuming if you had a pure cosine or sine type of waveform in it.
Yeah. So E's just like the losses we're getting. I guess we're just like that's the assumption.
Yeah, we're assuming that
Factor E.
we're putting in a sine cosine, pure sine cosine in there. Does that make sense?
Kind of.
What's your thought?
I don't understand how do we figure out. So we're saying it's dropping at a rate for the amplitude of E to the power of our attenuation
Yeah.
times the distance it's going.
Yeah.
So how do we find E as what's the rate it's dropping at? Is that just an assumption that we make in general, or does it change? Or is it always to the power of E to the power of?
Oh, I see what you're saying. It's always e to the power.
Always to the power. Okay.
Yeah. It's always e to the power. So for example, if I say I've got this length of line and the attenuation constant is alpha 1. This alpha 1 comes from the specifics of the R, L, C, and G. Okay? So every distance 1 over alpha 1, the amplitude decays by e to the minus 1, which is 0.36x. Okay, so if you had 1 volt into this lossy transmission line, 1 over alpha later, you'd only have 0.36 volts coming out. And if you do another 1 over alpha, so you did a distance, so this is L is 1 over alpha. If you had a distance of 2 of those, alpha 1, you'd get another 0.36x. Okay, so if you go 2 times 1 over alpha 2 distances, you end up with 0.36 times 0.36x, whatever is was your voltage in. So the amplitude is dropping as 1 over exponential of 1 over alpha. Okay. So generally after about 4 times 1 over alpha, so this is gonna be 0.36 to the power of the 4th, which is equal to 0.01. You'd say that like you've lost all your signal. So that's like as if you've lost 0.99x of your signal.
So is the attenuation really small value though?
Yeah, if you're lucky, yeah,
Because I was going to say that
Yeah.
seems like a big problem if you're dropping an exponential rate.
yeah.
For losses.
But it does depend. It's a small number, but again, it's like depends on your frequency and your distance. Like if you're running 10 gig transmission line, it won't be such a small number. Like you will lose a significant amount of your signal. Like people do not like run those lines on printed circuit boards more than 2-3 inches, because you just end up. It's not just a loss, but it's a big part of it. If you're on a silicon chip because of the substrate is silicon, which is a semiconductor, your losses are big and your lines are thin. So there, like if you're just running like millimeters and at high speed, you run into trouble. So it just really depends on the frequency you're in and what business you're working. And that just all depends on what business you're working in. Okay, so one last thing. Alpha is given in terms of NEPers per meter or dBs per meter. Or decibels per meter. All right, so that's the lossy. The main thing about lossy transmission lines that you guys should remember, well, let me see if I have a summary. Okay, so let's summarize here. So, conclusion. In a general case, we have all L, C, R, and G as transmission line coefficients. And in that general case, each section of the transmission line will have an impedance and Z. By the way, this Y just is called 1 over the impedance, is called the admittance. On purpose, I didn't add that to your grief, but just to, maybe you guys remember that. And the admittance is going to be G plus J omega C. And the impedance is going to be R plus J omega L. So this is each section. Of transmission line. And generally, gamma squared is Z times Y is equal to R plus J omega L times G plus J omega C and generally for forward going wave we're going to have something of the form e to the minus alpha z e to the minus j beta z. Let me get rid of this alpha, it's going to confuse us with the alphas. So reverse going wave. It's going to have a form of e to the plus alpha z, e to the plus j beta z. And 1 over alpha is called the attenuation length. And by the time you go wave has traveled by 4 times L alpha, its wave is gone to 0. And I'm happy to go through the details of this, but I'm just going to jump to the end of it. It's just a bunch of algebra. But if you guys, the characteristic impedance for lossless transmission lines is square root of L over C. We had that before. So the characteristic impedance for lossy transmission lines is square root of R plus J omega L over G plus J omega C. By the way, you guys can see how much this complicates life, right? Because before, this was just a constant, was not frequency dependent at all. And with the lossy transmission line, it is frequency dependent, because can't cancel these guys anymore. So anyway, the analysis gets more painful. And again, fortunately, for most transmission lines, for most cases, a lossless transmission line is a pretty good approximation until you really get out into the weeds. Okay? Do you guys need another break or should we keep going? Break? Okay. 10:15?